name is David Weigel, and I'm the planetarium director here, and I am very, very excited to host all of you this evening for this very special version of our Pass the Torch lecture series. And today we have Dr. Nikki Fox, who is going to be discussing the amazing journey of the Parker Solar Probe and some of her involvement in it. And so I'd like to welcome her to the stage right now. Thank you so much for joining us. Dr. Nikki Fox is the Director of Heliophysics at NASA and has been since 2018, 3 weeks after the launch of the Parker Solar Probe. And prior to becoming the Director of Heliophysics at NASA headquarters, she was the project scientist on Parker. And I will let her tell you a little bit more about herself, and then we will go ahead and get started. So thank you so much for coming. We're honored to have you here, and we're very excited as well.
Thank you. It's great to be here. This is my first time talking in a planetarium and with a live show. So we'll see how it goes, because I was a little nervous when they said I couldn't use my PowerPoint. And I live and die by PowerPoint charts. And so we'll see how that goes. I think it's going to be a fun evening, and we'll learn together. But I thought I would just tell you to start off with, so I have my background in physics. I did a bachelor's in physics, and then I wasn't quite sure I wanted to be a scientist. And so I went off and did a master's in engineering and satellite communications. And as soon as I got there, I was continually told that I asked the wrong kind of questions. I asked why, not how. And I was told over and over and over by my professors, you really, really, really think like a scientist. And so armed with that new knowledge, I went back to Imperial College and I did my PhD in space plasma physics. Shortly after that, I went to NASA's Goddard Space Flight Center as a postdoc for a couple of years, and then got hired at the Applied Physics Lab, and I was there for nearly 20 years. During that, I also had the privilege of being the deputy project scientist for the Van Allen probes. So they were 2 spacecraft orbiting in the radiation belts, and then shortly after that, I got the great opportunity to be the project scientist for Parker Solar Probe. So it was a very difficult decision to move down to NASA headquarters. I think it was a good time to go. As David said, it was just 3 weeks after the launch, and we were deep, for any of you who work on space missions, we were deep in post-launch blues as all of the teams started to move away and do other things. And so it was a good time, I think, to move to headquarters. And so I started there in September of last year, and I have been loving every minute of being there. And so I'm going to share with you a little bit about heliophysics. I guess it's time to go up the stairs. So I'm going to get to enjoy the show, because I'm going to come and sit up there so I can see what's happening. But we'll start off by telling you a little bit about what heliophysics is, and then some of the really great science that we do. And of course, my favorite mission, Parker Solar Probe, which I like to call the coolest, hottest mission under the sun. So we'll start by talking about what heliophysics is. And so heliophysics, broadly speaking, is one of the 4 science divisions at NASA. The others, of course, being planetary, astrophysics, and earth science. And so we're one of the 4. Thank you. I like to think, some people say, well, it's a new division. It's a word that was recently kind of made up to mean everything under the sun. But really, when I think about it, the heliophysics is probably the oldest of all of the science disciplines, because from the moment anyone looked up and saw the sun, they wondered what it was in the sky. There were lots of myths and legends driven by the sun. Of course, its impact on Earth, and just the constant need to know what that star in the sky is. And so we really think of it as the original science discipline. Of course, heliophysics is not just the study of the sun. It is the study of the sun and everything, all of the impacts from the sun. And so when we look at the helio portfolio, so if we can go to the sun and then bring up the rest of the fleet, that would be great. So when we start from the sun, oh, I'm sorry, we were going to do a countdown. Sorry, I forgot that bit. Okay, no. Live TV. No. Here we go. So we're lifting off from the Earth, trying not to feel too dizzy. The Earth disappears beneath us, and then we are go for the sun.
I can give you your observatories right now.
No, it's fine. So it's a beautiful star in the sky. It's about 93 million miles away. But it is, of course, the closest celestial object to us. And so even though it's very challenging to go and visit our star. We had to put up with a lot of great challenges on this mission. It is, of course, the star that we can most easily visit. And it has great impact also for us with astrophysics, because understanding the way our star works means that we will then be able to understand how other stars in our galaxy also behave. There are lots of stars that are very, very similar. And as we look for exoplanets and continue to search for life outside our solar system, getting a really good understanding of our star is really important. And so if we can look at the whole fleet, please. I like to call this my baby picture. All of my children together in the sky. And here we go. You can zooming into the through the various planet orbits into the star in the center. And now we'll add the Earth and the protective magnetic field that protects us actually from all of the stuff that comes from the sun. We are very blessed. We kind of live in the Goldilocks region, not too hot, not too cold, just perfect to sustain life. And that magnetic field that you can see here is actually protecting us from all of the harmful radiation from the sun. But this is our fleet of spacecraft that we use to really understand our star and then all of the impacts that we have here on Earth. I can highlight just a few of these. So ICON here, we're getting ready to launch in about 2 weeks. ICON will launch from Kennedy on a Pegasus rocket. It will basically join GOLD. GOLD is a hemispheric imager that's looking down at the Earth and looking really at the region where the terrestrial weather from below meets space weather from above. So it's really everything that is driven by our planet, the weather that we see here on Earth. As that moves up, it then meets in this region where everything that is driven by the sun, and where these interactions are happening, GOLD is kind of imaging that region, and ICON will be flying straight through it. So we're excited to see ICON coming up very soon. We have a lot of spacecraft that are out in the solar wind, that is out in this region between the sun and the Earth, very close to the Earth. They're only about 1 million miles away, and they orbit out here, and they're basically like little buoys out there telling us what is coming from the sun, so that we can predict better any impacts that we'll see here at Earth. Voyager, there are 2 Voyager spacecraft. They've actually both left our sort of protective bubble. Not only does the sun drive everything that we see here at Earth, but it also shapes our home in the universe. And so the sun, this continual streaming atmosphere that comes away from the sun, bathes all of the planets and goes out to the very edge of our solar system, where we see the impact of the sun kind of dying out and going down to a sort of zero effect, where it meets interstellar space. And so this also provides a boundary for us that really protects us from lots of the radiation and lots of the harmful stuff, cosmic rays, that come from outside our own solar system. And so the sun, as the sun orbits around the Milky Way, it's basically protecting us in this shield. And so Voyager is out on the very edges, telling us about what's happening in interstellar space. Parker Solar Probe up incredibly close to the sun, finally giving us all the information we need about these mysteries that we're going to talk about today that happen in the sun's corona. And so when I try and explain heliophysics to my kids and they say, well, I don't really understand what it is, and I say, I basically just think that Mummy is the Lion King and I control everything that the light touches. So with that, with that bad joke, we will go and maybe we could go to the sun and take a look at our star up close. So when we look at the sun, obviously you never look at the sun with your naked eyes, but if you look at the sun invisible, it looks kind of boring. It's just a fairly uniform disk. Every now and again you see some of these little dark spots on the sun, where they are sunspots. But really it's a pretty uniform looking disk. This is actually a particularly active sun, and this sunspot group is very, very powerful. But this is a fairly boring looking sun. But if we now can look at it with different wavelengths, we can see that a lot more action is seen as we move away from the sun. So this is basically showing you the magnetic field structures on the sun. These are opposite polarities. So if you think of this as a horseshoe magnet where the field is coming out one side and going in the other, and that is really what is under a sunspot. It is an incredibly powerful pocket of magnetic field, and so this is a nice way of being able to see where these really strong magnetic fields are. All right, so if we go to the next wavelength, please. And now looking at it in a slightly different wavelength, we're moving out, basically looking at the sun in different regions that really correspond to distances away from the sun. And so with each of these images that we show you, you're looking at a little bit further away from the sun. So this is the solar surface, and then now we're looking at an ion line, and we're looking further out. Each time we show you a different image, the temperature that it corresponds to is actually hotter. And this is our first mystery that we have at the sun. So first of all, you can see here just how active this star is. And so whenever you say, well, the sun is a constant, it's always constant in the sky, the moment you look at it in anything other than visible, you see very quickly that it is anything but a constant body. It is continually changing and continually active, lots and lots of great active regions. These are beautiful coronal loops here. So again, now you can really see these magnetic field lines. So when we looked at these little spots, here's the one we were looking at the front here. And you can see the way the field comes out and goes back in, just like a horseshoe magnet shape would be. Now, these loops can get extremely active. They can, as you can see, they're standing quite far away from the sun here. They can actually get pulled and pulled and pulled out until eventually they will snap, and that is what allows all of the energy in the corona to come out and can in fact impact our planet. We call those coronal mass ejections. They're basically a mass of coronal material that is ejected really fast, and that's what we're looking at when we see some of these really beautiful events on the sun. So now we're out at about a couple of million miles above the sun's surface, and we're now at a temperature of about 3 million degrees. So when we looked at the sun in visible, we were looking at the visible surface. Obviously, the sun doesn't have a solid surface, but it does have a visible surface. We call that the photosphere, and that temperature is about 6,000 degrees. And so now, just a million miles or so above the sun's surface, you're now looking at temperatures of about 3 million degrees. And so that really just doesn't make sense. If you have a hot body and you walk away from it, so if you're out camping and you walk away from the campfire, it certainly does not get hotter as you walk away from the campfire. It gets dramatically cooler. As we're moving away from the sun, we are seeing these temperatures increase by about 200, a factor of 200. And so that is a complete mystery. Why? What is going on in this solar atmosphere? What physics is taking place that is really giving rise to these incredible temperatures in the sun's corona? Now, you will have, if you were lucky enough to have seen the solar eclipse that happened in 2017, or indeed any others before that, but you would actually have been able to see the sun's corona for your very own eyes. And that is the only time that we can really see the sun's corona. We have to wait for an eclipse, which covers perfectly the disk of the sun, lets us see all this light that is really close. This is the chromosphere, and then out into the corona of the sun. And so part of where you were looking, if you saw this total solar eclipse, is actually the region where Parker Solar Probe will be flying. And so the beautiful images. Can we also go back to the sun and show the magnetic field, please? Because one of the things that we were really keen on measuring when we got close and when we get into the sun's corona is the sun's magnetic field. And so very similar to how the Earth has a magnetic field that is actually our protection, the sun also has a magnetic field. It is a lot more complicated than the one you typically see at Earth. At solar minimum, so the sun has a solar cycle, which is about 11 years. And at solar minimum, the sun's field is fairly boring. It's kind of like a dipole field. It looks not too dissimilar from what you would see at the Earth. It's a fairly simple magnetic field. But the equator of the sun rotates faster than the poles. And we think this is one of the reasons that the sun actually has a flip in polarity every 11 years. At the solar minimum, it's a very boring field. The sunspots are few and far between, and they tend to be at high latitudes on the sun. as the rotation at the center of the sun, at the equator, continues to go faster and faster, these magnetic field lines are rotating with the sun for a large amount. And that will cause the middle to get extremely confused. It causes a lot of very, very, very strange shapes, very strange configurations on the sun. It gives rise to a lot of these very active regions. You see the sunspots move down towards the equator as you get to solar maximum. And then basically it kind of flips in polarity and unravels itself for the balance of the 11 years. And so one of the really great things about the Parker Solar Probe mission is it's actually a 7-year prime mission. And so we are covering the full range of solar activity, covering both a solar minimum and then moving up towards a solar maximum. So that's one really big advantage for us. We're looking at very different types of solar wind, very different types of expanding atmosphere away from the sun. And so if we could go and look at some LASCO images, so we can look at what that corona is doing. So when we looked at the sun in the different wavelengths, we could really see a lot of those loops that are stretching out on the sun's surface. So now if we actually create an artificial eclipse, and so obviously we're scientists, we can't wait for an eclipse all the time to do our science. So we fly instruments that block out the light from the sun, so creating an artificial eclipse. So the white line here obviously is a illustration of where the sun would be in this disk. This disk is about 3 solar radii in diameter, and in radius, and it is blocking out the really bright light from the sun. And so now you can see some really interesting features. Number one, you see that the solar wind is continually streaming away, but there's a really nice explosion there, and that is those field lines, those loops that we looked at that are now being so stretched that they'll actually explode and let all of this coronal material, coronal plasma, come out. So this is superheated plasma. It's at about 3 million degrees, and it is ejected at millions of miles an hour. And so billions of tons of this material gets expelled every time we see these big coronal mass ejections. You also see some little white spots. This is not a glitch in the data or a problem with the movie. These are actually very, very energetic particles that get accelerated to about half the speed of light. It takes light 8 minutes to travel from the sun to the earth. These particles get to the earth in less than 30 minutes. It's about 25 minutes it takes them to get to the earth. And so it's one of the reasons that we have to be very good at predicting these big events, because we do not have a lot of time. By the time we have seen it, the particles are pretty much already at the earth. And so these particles are harmful to astronauts, particularly if they're out doing a spacewalk. And so we are always watching continually what is happening on the sun to be able to better protect our astronauts. Now, if we can go in for just a bit of a bigger view, we'll shrink the sun a little bit. And now we're going to go out to a different filter. So it's more of a wide field image. And again, the white line there showing where the sun would be. And now you can really see how big these loops are when they're exploding. It's a beautiful event coming out here. This happened in July of 2012. Some of you may be familiar with an event called the Carrington event. And so this was in 1859 that was the first time that we learned that profound effects that you see on the sun have a huge impact on Earth. And so there was a British astronomer, Richard Carrington, was sketching sunspots. He was looking through his brass telescope and sketching sunspots on the sun. And he'd been following this particularly large group on the sun as it moved across the disk. And while he was looking at it, he saw some very bright white flashes of light. He said they looked like fireballs on the sun. Just a few minutes later, they were not visible anymore, and so he didn't really think anything of it. But about 12 to 18 hours after he saw this event, compass needles at the Earth started to spin. The aurora was seen down towards almost equatorial regions, coming down visible from Singapore, from Cuba, and this is not normally where we see the aurora. Anyone who's gone to see the aurora, normally you go somewhere really cold to see it, and you're up around the Arctic circle, and so they had come down to incredibly low latitudes. It caused sparks to fly from the telegraph system. That was how we communicated in the 1850s, and it actually took down the telegraph system in the US for a number of days. And whenever I tell kids this, they look at me like, well, that's not really much of a big deal. And then I say, just imagine you had no internet for 4 days, and then they get really, really, really scared. And there would be no Xbox for 4 days. Oh my God, national panic. So, but this is a beautiful, yes, exactly. This is a very big event. And in fact, we were very lucky here on Earth that it went off on the side of the sun. And so you're seeing it sort of come out this way. And if we watch it again, you'll see there are several events. It's kind of a compound event. There's a really big one, and then you'll see a little loop come out. That's actually a third eruption. And so it was a compound event where the first one really sort of destroyed the atmosphere and cleared everything out. So when this second one came out, it had nothing stopping it. It was just blasting out. It hit one of our stereo spacecraft that were out in the solar wind, not particularly close to the sun, more in the Earth's orbit, but they were around looking at the backside of the sun. It directly hit one of the stereo spacecraft, which gave us great data in the solar wind. And when scientists went and modeled this event, what it would have done if it had hit our planet, then they estimate it would have been actually a bigger magnitude event than the Carrington event. And so, we do need to, it's very profound for us, we do need to be studying our star, understanding it, so we can better protect our life and society. In 1859, a telegraph system was damaged. In 2019, the effects will be much more devastating. Some studies have shown that we would maybe have $2 to $3 trillion worth of damage, and we could lose power for many, many months, particularly if we had transformers that were damaged. So it's incredibly important for us. We rely on spacecraft, on satellite technology, and those satellites are out orbiting in space, totally vulnerable to anything that comes from the sun. And so it's very important for us to really understand our star. And so we talk a lot, we've obviously all really just enjoyed the 50-year anniversary of Apollo. And so, we talk a lot about standing in the time before. And I think with the renewed interest of going back to the moon, going to Mars, and then beyond, we really are kind of standing in that time before. And it's very similar to right before the Apollo era, where everything was possible, everything was impossible, everything, the impossible needed to become possible. And so, the sudden increase in interest in space and interest in technology, I think we're seeing the same thing happening today. And so if I take you back to the time before, I would take you back to 1958. And so in 1958, a then young scientist, James Van Allen, had just launched, and you see James Van Allen here, and this is another scientist, John Simpson. So they had just launched Explorer 1, and they had discovered at this time that space was not empty. Well, the same year, a very young scientist called Eugene Parker published a paper where he predicted that this solar wind, in fact, he actually called it a solar wind, would continually stream away from the sun. It would stream out of the corona and bathe all of the planets and actually shape our heliosphere, shape this protective bubble that we have that is actually protecting us from interstellar space. And so he predicted that, and it didn't, to put it lightly, the paper did not go over very well. He had a lot of negative opinions about this paper. There are two main mysteries that the solar probe was really designed to address. One was this weird coronal, what we call the temperature inversion. So as you move away from the surface of the sun, you would expect that temperature to go down, and yet in our solar atmosphere, it's going up. And it increases until it gets to this maximum of about about 3 million degrees. And that's just something that shouldn't happen. It's like water flowing uphill. It just doesn't happen. And the other was, why is this solar wind continually accelerated? Why doesn't it, if you put energy in somewhere here in this region, why doesn't it just slow down as you would expect it to slow down as it moves away from the sun? But it doesn't. It continues to be accelerated. It continues to move at very fast speeds of about 1 million miles an hour or more away. And so it's continually streaming away from the sun. And so the only way we've looked at the sun in every different wavelength, and maybe we could do our cool thing on the dome. So we've looked at the sun in every different wavelength, and we found amazing things about it. Actually, by looking at the sun in different wavelengths, that's how we discovered that the temperature was so much higher. And so when they were first looking at the sun using spectroscopy, they would find these really weird lines, and they thought, what is this corona made of? And so at first they thought, hey, we found a new element, and they called it coronium. And then more scientists started looking and saying, I think it's an ion line, but it's so energetic, it's got so many electrons that have been stripped off from this iron that it has to be at these incredible temperatures. And so that's how we discovered that the corona was actually 300 times hotter than the sun. And this is a beautiful thing. If you wait for this one is visible, so if we wait till you get here, you'll see how boring it looks invisible, and then just how amazing it looks when you put it in the other wavelengths. And so we've looked at the sun in literally every wavelength possible. We've sent spacecraft out into the solar wind as close even as the planet Mercury. But really, by the time the solar wind gets to Mercury, all the action has happened, all of the magic has already occurred much closer to the sun. And so we really did need to kind of brave the frightful journey and develop the technology that would let us fly a spacecraft right into the sun's corona, to be able to really sample what is going on there, what physics is happening. Is it one theory that we have, or is it another theory? Is it a combination of many different theories? And so we really need to understand the physics of close up to the sun. And so let's take a look at some of the technology that allowed us to be able to fly this daring mission. Because it's a beautiful shot. It's a beautiful shot of the sun. So no, let's do a flyby. It's a cool thing. So this is a beautiful shot of the spacecraft from behind going in towards the sun, and there is a nice animation of the solar wind coming out and hitting the spacecraft. So the spacecraft will be going in very close to the sun and doing a fabulous job. We've already done 3 flybys, and we have amazing data. I'm going to show you a little bit of the data towards the end of the presentation. But there is Parker Solar Probe, nice and close to the sun. All right, so if we can look at some of the technology. So actually, if you can bring up the 3D spacecraft, we will look at some of the features on there. So one of the things that is very striking about the spacecraft, it's hard to see just looking here, but it really is how small the spacecraft is. She stands at just 3 meters from stem to stern. At her widest point is the heat shield, obviously, because that is giving us shade for all of the other instruments, so they do not have to deal with the incredible temperatures that we're going to see close to the sun. So this is about 2.3 meters in diameter, but the main body of the spacecraft here is about 1 meter in diameter and about 1.5 meters tall. So that's actually an incredibly small spacecraft bus. You'll see, we'll show you a movie of us putting together the spacecraft in a little bit, and you get a good perspective for just how small she is. But if we can turn her around so we can look at that heat shield on the front, that would be great. And so that's a 2.3 meter diameter heat shield. You notice the slightly odd shape of it because we have little cutouts to make sure the instruments are all protected. But the heat shield is about 8 feet. We call it our 8-foot frisbee because it's about 8 feet in diameter and just 4.5 inches thick. It weighs about 100 pounds. So one of the things that was important for us was not only that we needed to be small, but we needed to be very lightweight. And that is because when we leave the Earth, we want to move with incredible launch energy. And so we don't want to be in any way dragged around by the Earth as the Earth orbits the sun. We want to leave any influence that the Earth has over the spacecraft and just turn in and go directly to the sun. And so everything, we used to joke we were the team that was always on a diet because we daren't put a pound on. And so the spacecraft, you can see this beautiful white coating on the top. So this is a whiter than white coating. It was actually made specially for the Solar Probe mission. It was developed at the Johns Hopkins Whiting School, and it's basically like a ceramic coating. It's an alumina coating, and it's plasma sprayed on because one of the things we want is for it to be incredibly flat. We're never going to get it totally flat because it is like an alumina, but we need to get it as flat as possible because you want to keep it with uniform illumination as it's coming into the sun. The heat shield itself is made of a carbon-carbon composite, and so it has two very thin phase sheets that are made of like a carbon-carbon composite. It's a bit like a graphite epoxy that you would find in your golf clubs or a nice tennis racket. And then, I don't know if we can turn it on its side so you can see this side, but here, oh, that's beautiful. So here is about 4 inches thick of a carbon-carbon foam. And that actually has the consistency a little bit like forest foam that you would find, if you get a flower arrangement, they have that horrible green florist foam in it. And just, it's got that kind of real consistency. It's about 98% air when it was here on Earth. Obviously, out in space, we lose that air and it becomes a very rigid structure. And so that is our heat shield. That was probably one of our biggest technology developments. As we go close into the sun, I mentioned that we will be going through 3 million degree plasma. But fortunately, we do not have to deal with temperatures of 3 million degrees. What is very nice for us is the solar wind is not very dense. So there are very few particles to actually be able to couple into our heat shield. And if you think about if you turn your oven on at home and you put it on to like 500 degrees, you can put your hand inside the oven and hold it in there without any problem as long as you don't touch anything. So the moment you touch a rack, you actually allow the energy to couple into your fingers, and that's when you get burned. But you can actually put your hand inside the oven and you feel hot, but you won't get burned. You're not at that temperature. And so that's very similar to what Parker Solar Probe is experiencing. So even in 3 million degree plasma, there's not very many particles, and so very little energy is actually coupling into the spacecraft at all. The main thing we have to deal with is light from the sun, is actually the energy from the photons itself. And so that's one of the reasons we put a whiter than white coating on. And as we remarked today, I was very happy that Jim had rented us a white rental car and not a black one as we came out, and it had been sitting there all day in the blistering sun today. So a white coating, obviously far better off at reflecting a lot of the light away from the heat shield. But at our closest approach, the front side of the heat shield will get to temperatures of about 2,500 degrees Fahrenheit or 1,400 degrees Celsius. But the instruments that sit on the main body of the spacecraft, they're at a temperature of about 80, 85 degrees Fahrenheit or 30 degrees centigrade. So not quite, maybe a late fall day for you. Definitely not the temperature outside today. But anyway, so that was one of our biggest challenges was getting that heat shield to be able to deal with these temperatures. Not only, you'll see when we show you the trajectory, the spacecraft also gets very cold. The orbits are highly elliptical. They go close into the sun on one side, but then come out around the orbit of Venus. And so out around Venus, it's really cold. It's in the full cold of space. And so it's not just a case of having something that can deal with incredibly high temperatures. It's actually having something that can go very hot and then very cold over and over again as we do our 24 orbits. And so if you think of any material that you can think of, if you heat something up to a very high temperature and then cool it rapidly and do that over and over again, most materials will change their property. They'll either become very brittle and flaky, or they'll become elastic and kind of, get a sort of plastic deformation. And so it was another challenge to come up with materials that would be able to go through these incredible temperature swings and actually be able to withstand it. So the other thing that was very important for us was to be able to actually connect this heat shield. And you can see a nice shot here of this is a titanium welded structure, and this holds our heat shield in place. And so there are so many complicated things about this heat shield, but you'd think a heat shield would be simple, but it really isn't. And so another big challenge is how to attach it. So now you've got a titanium welded structure that is going to hold the heat shield in place, but how do you attach it to this truss? We wanted to attach it with the minimum amount of contact to actually stop any heat being convected from the backside of the heat shield into the structure. And so it is actually connected with just 6 carbon bolts. And you can actually see a nice shot here. We call these the pie pans because they're like an inverted pie pan shape. And that's how we connect into this truss structure. So 6 carbon bolts come down in the 6 attach points and hold that in place. Another big challenge is, due to this incredible change in temperature, the heat shield is going to change dramatically in shape. And again, you think when you heat something up to incredible temperatures, it expands. When you cool it, it contracts. And so our heat shield is going to be doing all kinds of different shapes and different, it'll sort of deform in different ways as we go in and out on our orbit. And so each of these pie pan structures is really more like a shoulder joint. So if you imagine how you can move your shoulder and you can move your arm in all kinds of different directions, and whichever way you put your arm, your shoulder copes, your arm doesn't pop off if you put it in a weird position. And so that's exactly what we have here with these. They're very much like shoulder sort of ball and socket joints that allow this heat shield to really deform on orbit. So the other really useful thing that we have on our titanium structure here, you see these black fins. That is our solar array cooling system. And so it sounds kind of ironic when I say one of the big challenges we had was using solar power to go in to do this mission. Original concepts, there have been many over the 60 years that it took us to get this mission off the pad, but there have been many different concepts, and most of them use some kind of RTG or some kind of nuclear power source. When we were getting ready to design this mission, NASA gave a challenge to the Applied Physics Lab, Johns Hopkins Applied Physics Lab, to be able to do this mission without doing a Jupiter flyby and without using any kind of nuclear power. And so, of course, that meant we were going to use solar panels, and you can see our solar wings stretched out here on either side. Now, I often get the question, well, why is that a challenge? I mean, you're going to the sun. Surely to God, you'd want to use solar panels. But of course, as we all know, any of us who have accidentally left our phones or any kind of electronics on the front seat of a car in a very hot day, electronics do not like to get hot. And solar cells are exactly the same. And so we have to find a way to keep them cool. So if we can actually look at the solar wings. So here are our solar wings that stick out on either side of the spacecraft. In between each of these solar cells, we run a coolant, and it's actually water. And yes, it's just plain water. It's not anything exotic. Water is an incredibly efficient cooling system. And so we run water through each channel between every single one of these solar cells, and there are many, many, many solar cells in different lines, different rows here. The other way, so once we've run the water through the solar cells, we then actually get rid of the heat from these radiators that are also held on this big assembly structure. So this titanium structure is very important for us. The other thing that we do is we actually tuck our solar panels away when we get close to the sun. So when we're out around the planet Venus, or even just leaving the Earth, we have the solar wings at full stretch. As we get closer and closer, we pull them further in. These also are on kind of shoulder, a bit like a shoulder joint. They can flap and feather, and so we can turn them to get maximum sunlight when we need it, and then tuck them all the way in, and so it's just that very last knife edge of cells that is sticking out and actually can get some illumination. And when we're at closest approach, that very last row of cells gives us the same amount of power as the full wing does when we're at Earth. And so, it kind of also gives you an idea of just how close to the sun we are. And so that's some of our major technology that we have right there. I guess we could look at, can we run the video of us putting the spacecraft together? It's probably a good time to do that. And so you'll see us starting, so the spacecraft was built at the Applied Physics Lab, and all the instruments were integrated there, and actually we did a lot of our testing. So this is the main structure of the spacecraft, and you can see how small it is. That is the spacecraft bus. This is us lowering, this is changing the pointer. Oh, yes, thank you. So this is us lowering the top deck onto the spacecraft. So there you get a nice shot of our cooling system. This is them bonding our heat shield. So that is the bottom phase sheet, and this is the foam that they've just put on top. And then they flip the whole thing over and put the other side in. This is the most terrifying sight I've ever witnessed. This was the vibration test of Parker Solar Probe. It is not for the faint of heart. Neither is seeing your spacecraft lifted up 4 stories high, hanging by a few wires, and lowered into a thermal vacuum chamber. But as I say, the space business is not for the faint of heart. So we did our testing at Goddard Space Flight Center, and then we had a nice ride, courtesy of the U.S. Air Force, down on a C-17 down to Florida. And so here we are at the Astrotech facility, doing the final touches before she launches. And so they were the solar panels going on in their protective cover. Here is the heat shield going on, and you can see those very nice shot there of those attach points, and there she is looking very beautiful. Shortly after that, we lifted her up and installed her on the 3rd stage. That is our final kick motor that we use right after launch. And there she is in her 40-foot, very blingy, tricked out fairing. And here we see her on the Delta IV Heavy on the launch pad. And I don't know if we can get that last shot back, but one of the things to give you an idea of scale, just run through it again. I missed a couple of things. We'll go through it again. It's fine. But when you see that rocket at the end, you will see how small she is. The logo on the side of the spacecraft is about the same size as the spacecraft itself. This is by the way, this is the harness. So this is all of the wires, all of the cables that need to make Solar Probe work. And so again, you see this nice shot of this cooling system. And so that was the foam that you saw, and they're lowering the foam now onto that phase sheet. And that is the backside of our heat shield. Once again, the terrifying sight. It's very, very noisy. It's very, very scary when you see that thing vibrating. So I mentioned that we did our testing at Goddard. One thing you'll notice when she gets into the chamber is she does not have a heat shield on. And that is actually because the heat shield goes through a very different test regime than the rest of the spacecraft. Obviously, the rest of the spacecraft does not have to deal with those incredible temperatures. And so we don't want to expose them to those temperatures in thermal vacuum. So the heat shield was actually tested separately. And then that's actually why you see it coming second. Here it is. The heat shield didn't get the fancy ride on the C-17. The heat shield came down by truck. But again, you see the attach points as we lower the heat shield down. The solar panels there, now you can actually see the solar panels. There's that very last row of cells. You see how small it is compared to the rest of that last row is what's giving us our power when we're close to the sun. And so another nice shot of, never get tired of looking at this girl. But anyway, so if you look at the logo on the side, great. The side of the spacecraft there, the spacecraft itself, the real spacecraft, is about the same size as the spacecraft on the logo. And so when you look at the mighty power of a Delta IV Heavy, she literally looked like a hood ornament on the top of the rocket. She's just about here in her fairing. One thing to note over here, this is the planet Venus. And so we stood here just actually pretty much where you'd think we were standing looking at this picture. We stood here as a team to say goodbye to Parker before she launched. We were all very, very sad, but then we looked up and we saw Venus in the dusk sky, indeed welcoming her because Venus was her first stop. We were all a bit teary on the first night, and so then she didn't launch, and we all felt guilty and thought maybe it was because we didn't want her to go. So we went back the next day and had a chat with her and said it was really okay and she should definitely launch. And so we were very happy that on our second launch attempt, and if you have some launch footage we can look at, but you see a beautiful shot of the Delta IV Heavy right before launch. So we launched on August 12th, which only fitting was a sun day. And there she is. I know I'm full of puns today. And so there she is on the pad about to lift off, I think. It's a beautiful sight as she lifts off. Delta IV Heavy takes a while to get off the ground. It's not something that is for the faint of heart. You see the flames, you see all this starting, and then nothing's happening, and you do start to wonder if something's gone wrong. And then the flames get more and more and more, and she still hasn't lifted off. There's that moment of panic, and then indeed she finally lifted off, an incredibly graceful lift off into the sky. It is a beautiful launch. So that was 3:31 in the morning. My team tells me I'm bad luck because we always have to do nighttime launches and nobody gets any sleep. And then believe me, on the second launch attempt, really no one's had any sleep. But it's a beautiful shot of those the three Delta engines moving. So when it first lifts off, the two are going at full power, and then as they start to run out of fuel, they throttle back, and the middle one comes on and really takes over to give it the final boost out of our gravity and out into space. But just an absolutely gorgeous launch. And yes, I could watch that over and over and over again, and I do all the time. So yes. And so I don't know if you have the video of her trajectory that we can show you. So basically, she blew through all of the first stage, and then we had a second stage, cryogenically fueled rocket that then fired. And then you saw that final upper stage, that actually gave her about 80% of her delta V, or 80% of her launch energy. And so that's fine. It'll come from here. I told you I can watch the launch over and over again. It's fine. It's not a mistake. So you'll see as it lifts off that one of the first things that happens is the fairing opens, and Parker Solar Probe is indeed out of our atmosphere and in space. So here's the fairing opening. It's very nice. And then you see that second stage cryogenically fueled rocket there. She separates from the second stage, and here you can see now a great shot of our upper stage. Of course, this is all a artist's animation, but there you saw that kick motor firing, giving her 80% of her delta V. And then she separated from the final stage and indeed went off towards Venus. The first thing we do is put out those solar panels to get the power, and then we deploy anything that was kind of tucked in or folded away for launch. Obviously, we want to protect all our systems, so there are some of our science instruments coming out. Now, she is moving very fast. She's already broken all speed records, but she's moving incredibly fast. And just 7 weeks after launch, she encounters the planet Venus for the first time. We do a gravity assist around Venus, and that really helps us to focus the orbit in towards the sun. As I'd mentioned, we don't want in any way to be orbiting around with the Earth. We don't want the Earth influencing this spacecraft at all. And so we use Venus to give us a little bit like a handbrake turn and really focus us in towards the sun. And so you saw there a nice shot of those solar wings tucking back as we get into closest approach. They will tuck back, and so that's just that last knife edge of cells that is sticking out. And so there is Parker Solar Probe doing one of her flybys of the sun. And so I think you have a nice animation of the trajectory that you did for me. But we can see there are 7, she flies past the planet Venus 7 times during the 7-year mission. She does 24 orbits. The mission is designed so that 7 of those, well, the first one obviously was right after launch, but then there are 6 others that bring her very close to the planet Venus. And so we are able to use Venus to continually shrink our orbit. And so I always like to say we're not like those other planetary missions that take energy from the planet. We generously give to Venus. We're givers in heliophysics. And so we give energy to Venus, and we use Venus to slow us down just a little bit and to That allows us to orbit closer. You see that orbit shrinking with each time we do a Venus flyby. And so right now we've finished our third perihelion pass. We're about here right now. And then on December 26th of this year, we will do another Venus flyby, and that will then shrink our orbit into this second petal. And so we'll do 6 more of those until she gets incredibly close to the sun. It's a really cool mission for many reasons, but having these sort of 7 stages of the mission, it's almost like having 7 different science campaigns, because as we're going in, we are going through very different plasma. And so as we're in our first orbit, we're actually co-rotating with the sun. And so what that means is the place that Parker Solar Probe is sitting over, Parker is moving at roughly the same speed as the sun is rotating, which means that she's really hanging over the same piece of the sun for the whole of that first flyby. And so we really are sort of flying down one of those field lines that you saw when we added the field lines to the sun. We're really flying down one of those field lines, sitting on it and rotating around with it, and then flying out along the same field line. So it's really, really interesting science from the very beginning. And then, of course, we continue with those 6 further Venus flybys to walk closer and closer to the sun. And so this is an animation of us flying past Venus, and you can see the way she kind of turns. It really focuses the orbit in towards the sun, again, making sure that we do not get pulled out in any way affected by the Earth. And so very nice shot of the spacecraft there. And so one other big technology piece for us, obviously, getting her light and compact, we had to wait 60 years really for components to shrink. And if you think about the technology that you hold in your hand with your iPhone, whether some of you have already got your iPhone 11 or some of us are still dealing with our 8s, but you just think of the sheer amount of technology that you hold in your hand with your iPhone. And if you think in 1958, if you wanted to make a phone call, you had a rotary dial phone. And if you wanted to use it in a different room from the kitchen, you just needed a really long springy cord on the handset. And that was really the technology that we had. Now, if you think of everything that you do with your iPhone, I mean, honestly, you probably use it for everything except making a phone call. I tend to feel that I've had some breakdown in my life if I actually have to resort to a phone call and I can't use an app to solve my problems. But we really use those for absolutely everything. You use them for navigation, you play games on them, you check the weather, you do absolutely everything on that phone. But if you think in 1958, the amount of circuitry and electronics it would take to enable you to do that would be a few city blocks worth of buildings. And so again, getting things that are light, compact, small, miniature is something, and that's another reason that we've had to wait so long. One other thing to bear in mind is as she is moving past the sun, she's moving incredibly fast. We have to make sure that heat shield stays between the spacecraft body and the sun at all times. Now, it takes light 8 minutes to travel from the sun to the Earth. And so if this spacecraft has a problem, there is no way that we can get a signal from the spacecraft to Earth, have somebody think about what the problem is, and send a command back. It would be game over at that point. She would not be facing the right way anymore, and sunlight would actually hit pieces of the spacecraft that are not designed to see sunlight. And as you can imagine, bad things would happen. And we have our final closest approach, about 30 minutes of grace period on this spacecraft. It's not long enough to be able to do anything. And so we had to think about every single possible failure mode, anything that could go wrong with this spacecraft, and program it into the spacecraft itself so that anything that happens, she can take care of herself. And so one of the things we have are little sun sensors that are around sort of the back of the body here. None of them should ever see sunlight. So the moment one does, the spacecraft knows that she is not pointing in exactly the right direction. By knowing which one of the sun sensors is seeing the sun, she knows which sort of sequence of thrusters to fire to quickly turn her back into the right orientation. And so every single failure mode we had to think about before she launched. So she really is the most autonomous vehicle to ever have launched. I always like to say she's a tough, independent spacecraft. And she is, of course, faster, hotter, and closer than anything else has ever been. I mean, we're not competitive at all, but, we're just faster, hotter, and closer, and totally cooler than anything else. But I'm not biased. And so, we talked about hotter. So, she's in 3 million degree plasma. She's dealing with these incredibly high temperatures. So obviously we're going to be hotter. We're going closer to a star than anything else has ever been. But faster. So I said she's moving really very fast. Oh, no, we'll do closer. So I say, can you pause it? Okay, so I say, often when we talk about the closest approach, and I say, oh yeah, and it's really, really close to the sun. It's getting to within 3.9 million miles of the sun's surface, and I have people that look at me and go, well, I thought you said it was going close. 3.9 million miles. What are you getting all excited about? And so what I like to do is liken this distance to a football field, something that I know that we are all very familiar with. And so if I pop the sun and the earth, we can run it, in the end zones of a football field, and then we'll orient you with some celestial objects. So there's Mercury at the sun's 35-yard line. There is Venus at the earth's 28-yard line. Some of these beautiful coronal loops that we've been looking at can get out to about the 15-yard line. This is Helios 2. So up until Parker launched, this was the spacecraft that had come closest to the sun at about the 29-yard line. Parker Solar Probe is at the 4-yard line. And so even though 3.9 million miles might not sound that close to you, when the Earth and the Sun are 93 million miles apart, when we put it on this scale, she is just 4 yards away from the Sun. And so totally in the red zone, knocking on the door for a touchdown. Let's go, Bama. Did I pick the right one? I know it's like a 50-50 shot here, whether I should have said Auburn, but I usually say Ravens, but I know none of you will like the Ravens, so I bleed purple and black. So anyway, so you see just how close she is to the sun, really in this region where all of this action is happening, where all of this acceleration is going on. And so, Gene Parker had predicted that we would see this continually streaming atmosphere. It was a few years after his paper was published that a spacecraft, Mariner 11, was actually out in the solar wind and detected this continual streaming of this atmosphere and actually confirmed that Gene was right. But we've never been able to go in close enough to really determine what is causing this continual acceleration or what is causing this coronal heating. And so this is why we've had to send Parker on this really, really, really daring mission into the sun. So I did also mention faster. So right now she's moving at a reasonable speed. Her closest approach speed right now is at about 215,000 miles an hour. When she gets to her final orbit, to that 3.9 million miles above the sun's surface, she will be traveling at a blistering 430,000 miles an hour, which is about 118 miles a second. And again, she's got to keep that heat shield between her and the sun at all times. And so, I don't know, I think it's a bit like taking a bend too fast on an icy road, and you're going to have to fishtail your way to control that skid. And that's basically what she's doing as she is orbiting around the sun. And so clearly breaking lots of records. We broke the speed record, and then also obviously the closest to the sun. And so where is she today? I think that's what we're going for. So this is the trajectory, and then we've got a nice visual of showing, this is a beautiful image actually. You can really see how that perihelion, how she is stepping closer and closer to the sun. But so she's completed 3 of her closest approach already. And so right now she is about, let's see, that's Venus. So she's about here. And she's getting ready to come around, and then, as I said, on December 26th, she will fly past the planet Venus again, and that will take her to her next closest orbit, which is this one. So we're excited about that. I think there's only one in that configuration, 1 or 2, and then she does another Venus flyby. And so we're moving pretty quickly through these radial distances to get closer and closer to the sun. But as I say, this one was incredibly interesting because we did go into that period of co-rotation where we were literally sitting over the same part of the sun for days and days. And that's a pretty unique thing to be able to do. So why don't let's look at some data. We'll look at some data. And so, beautiful shot of the sun in the background there. And so why don't we bring up the first light image? Yeah, good choice. So this is the first light image here. And so this, of course, is not an image of the sun. It is an image of the Milky Way. And actually, we probably should have looked at the instruments first, but we'll go with this one first. And so we have a white light imager on one of the sides of Parker Solar Probe. And that imager is not looking at traditional images of the sun as you have seen them in the beautifully here displayed on the planetarium screen, but it's actually looking at the structures that are right in front of Parker Solar Probe. So essentially, what are we about to plow through? And so this is a more typical image of something you would see in the solar wind. But this had a good story with it. This was our first light image. So we opened the door of the camera, and the first thing we took a picture of was the Milky Way. And the principal investigator for the camera, Dr. Russ Howard from the Naval Research Lab, he was actually very perturbed by this because he didn't realize that we were not facing the sun at the time. And so he actually was a little panicked that maybe something had gone wrong. Either the spacecraft was not pointing in the right direction or maybe his instrument was on backwards. And so he called me up and said, I don't know how to tell you this, but we're looking at the Milky Way. And I said, yes, that's because the spacecraft's on its side right now. And because when we're far away from the sun, we actually have to worry about keeping the spacecraft warm. It's one of the ironic things that we were actually almost more worried about the cold of space than we were about the intense heat of the sun. And so this is just a nice shot of where this would be in the sky. You can see the rest of the Milky Way up there. And so we had the spacecraft tipped sideways to keep some of the instruments warm when we were first out on orbit, because we hadn't even reached Venus at that point. And so it was perfectly understandable for us that we were looking at the Milky Way, but Russ was a little panicked about that. So let's maybe look at some of the instruments. Can we go back to the 3D spacecraft? Great. And then I'll tell you about the instruments which will make the data more meaningful, although it's only wiggly lines, but we're scientists and we get excited about wiggly lines. So here is the anti-ram facing view. So when Parker is in very close, you saw that she kind of does a sideways, she goes basically sideways through the corona. And so this is the anti-ram side. This is the side that looks away. So everything else is, most of the instruments are on this side. But if we look here, you can see two of the instruments. This one up here is the Solar Probe Cup. I hate to say it's a relatively simple instrument because it was a huge technology development for us, but it's a Faraday cup, so it's a fairly simple instrument. It's flown with one of the first space-borne instruments to fly, but of course this takes no shelter from the heat shield. I always call this one the bravest little instrument on the spacecraft because she literally peeps out around the heat shield and is in the full solar environment. And so this was a huge challenge for us to be able to find materials that, again, would withstand those incredible changes in temperature. Worrying about keeping this thing warm when it's out around Venus, and then worrying about the intense light from the sun when we're in very close. And so we had to use a lot of very exotic materials. It became apparent very early on in the development that the standard materials that the team had thought of using were not going to quite cut it. And so it has some sapphire rods in there. A lot of it is made from titanium. It is also niobium. There is molybdenum in there. There are all kinds of very, very exotic materials that are in there. I'll also point out here, this is a damping system that we had to put on. As you can imagine, the ride to space when we launch is not quiet and it is not smooth. It is a very, very noisy, very bumpy, and it will vibrate the heck out of the spacecraft. That's actually why you saw the spacecraft having that vibe test in the lab before we launched, because we really want to simulate all of the conditions, all of the really bad conditions that the spacecraft could have to endure on her way to space. And so launch is clearly the most terrifying and the most dangerous piece of the mission for us. And so this is a damping system that was built by Moog. It's very similar to a lot of the damping systems they use on racing cars. But that helped us to damp out the oscillations and basically stop the instrument shaking itself to bits as we launched. Obviously, we also blast it with sound. We put it in acoustic acoustic chambers, and so we really are simulating the voyage to space. I'll just point this one out here as span B, and then if I ask you to flip over the spacecraft, you will see her sister instrument, which is span A+. And so span A+ there has 2 heads on it. It is a little hard to see, but it's okay. Has 2 heads on it, and that is allowing us to see both ions and electrons. Span B on the other side is just looking at electrons, but if we take the 2 fields of view of the instruments, they basically fit together like the seams on a baseball, and so it gives us a full 360-degree view of the solar wind. So we want to be able to really see electrons traveling in both directions. It's important for us if you have a closed field line. So if one of those loops that you see is attached to the sun at both points, you expect to see particles flowing in both directions. And so when we're in close, we want to know if we're on these closed field loops or if the loops have already exploded and this have sort of given rise to the solar wind. So these 2 are electrostatic analyzers. They were both built at Berkeley, and are doing. You'll see some data from these guys in a minute. This is ESIS, so this is our high energy particle suite, and so that's really focused on focused on the high energy particles that are associated with transients in the solar wind. So I showed you some. We can look at a flare in a minute, but I showed you some of those coronal mass ejections. Because they are moving faster than the ambient solar wind, they create shocks in front of them, very much like a bow wave in front of a boat or a supersonic shock that you'd hear when a plane beats the speed of sound. And so these are really focused. They're high energy particles. We saw them a little bit in the movie where we saw the big event that happened in July of 2012, and you saw those little dots coming out. They are the very high energy particles traveling at about half the speed of light. And so this instrument is really looking at that population. And I like to think of the solar wind kind of as a river that's continually flowing away from the sun. This would be the speedboat that is floating across that river. It's a different population that is highly energized. And so really that's our third mystery. We talked about the coronal heating, the continual acceleration of the solar wind, but also what is causing these very high energy particles to be accelerated to half the speed of light. And so this suite here is really helping us to do that. This is WISPR. So this is the camera that took that Milky Way image. It's actually a little bit like a coronagraph. So the coronagraph that we talked about, where we blocked out the light from the sun and allowing us to look at the hazy. Oh, that's beautiful. There is WISPR. That is fabulous. So WISPR sits up here, looks sort of just out around the heat shield, but is completely within. If you think about the shadow, she is it goes this way. That's a beautiful shot of it. So you can see how the shadow from the heat shield is really protecting all of these instruments. So nothing sticks up above that protective shield. So this is WISPR here. It's 2 cameras, and so that allows us to look at the solar wind. So it's, as I said, it's a bit like a coronagraph in that it's looking at the solar wind structure itself, just like the coronagraph looks close to the sun. But this is really focusing on what the spacecraft is about to plow into. It will help us. The data are extremely difficult to analyze, as you can imagine. We're going into a region that we've never been before. We're going into really what I would argue is the most important, but certainly the last region of our solar system to really be explored, and that is the sun's corona. So we really didn't know quite what we would find there. And so this imager is really helpful for showing what type of structure that we're flying through. There's a really nice shot there of the ESIS suite, and there is span A+ on the side. So now we can see here also these are the electric field booms. So these are part of our fields suite. And so we want to look at all the electric fields and then also the magnetic fields. We showed you at the beginning just how complicated the sun's magnetic field is. So clearly we know the magnetic field has something to do with these incredible processes that are going on causing this acceleration and heating. And so we want to make sure that we really measure those magnetic fields. But wherever you see magnetic fields, when you see those changing, you see changing electric fields. And those electric fields can give rise to plasma waves. And so we are looking here at the electric field antennas, and they allow us to really sample all of the wave populations. So you may be familiar with it. some of the wave populations we have here on Earth, like Whistler mode waves. Well, there are very similar, there are electromagnetic waves, there are Alfvén waves, there are all kinds of different turbulence features. And so by being able to detect what kind of waves we're seeing will help us, again, to be able to really understand what is going on. At the back here are the 3 magnetometers. So they are our magnetic field instruments. We carry 3 because we know that the different types of magnetic field we're going to see as we go close and far away, it's going to be incredibly dynamic, and it's going to have a really, really, really big range of frequencies. And so one instrument alone cannot give us the frequency range that we need, and so we fly 3 of them. They are all looking at slightly different frequencies. There is a search coil magnetometer on the very end that is looking at the AC fields, so the very high frequency magnetic fields that we may see. And then there are 2 flux gate magnetometers that are looking at the DC fields, or the low frequency fields. We fly 2 of those, really so that the inner one can detect any waves or any magnetic field structures, any sort of perturbations in the magnetic field that are caused by this spacecraft. As you can imagine, you saw there was a lot of wires, a lot of harnessing, there's a lot of currents and things that are flowing just inside this spacecraft, and we want to make sure that we do not in any way compromise our magnetic field measurements. So basically the inner one is really sensing what the spacecraft is seeing, and then we can subtract that from the measurements of the 2 outer ones. And so that's really giving us incredible high fidelity measurements. You also notice how long these antennas are. Again, it's not easy to fly these things, but we need to get the probes are on the very end of these antennae. And we want to get them as far away from the spacecraft as we possibly can, so that, again, we are sampling the solar wind, and we didn't spend all this money to sample the electric fields that are on the spacecraft. That would be a terrible waste of taxpayer money. And so that is our instrument suite on the spacecraft. We do look at all of the plasma. So we look at the very low energy plasma that makes up kind of the bulk solar wind. And we can measure the temperature, the density, and the speed of that solar wind. And we can also measure the components. So we can look at how much of it is driven by electrons, how much of it is driven by hydrogen, by alpha particles, by helium, and then by some of the other heavier elements that we see in the solar wind. So we do a really good job of sampling all of that. And then the ESIS suite here, again, is looking at those very high energy particles that kind of float across the top. And then with our field suite, we're looking at the full range of dynamic, electric, and magnetic fields. And then last but not least, our Whisper camera. And so let's now we've looked at the instruments, let's look at some data. Okay. And so this is an initial image from the Whisper camera. And so this is showing us a beautiful structure here. You can see how quickly the spacecraft is moving, because you can see planets and anti-planets in this image. The images are taken about 12 hours apart. And so you can see how quickly the spacecraft is moving, how quickly the planet is moving in the site. Do you have the video too? Yes, okay. And then we can show you the video as it's moving through. It's a nice, it's taken over the full, oh, okay. So this is, oh yes, this video, that's what I wanted. Yes, this is perfect. So this is a beautiful representation that David's done of kind of moving the field of view in as the spacecraft view is changing. But there's a lot of structures that you see okay, so there's a lot of structures that you see in the solar wind that are very, very close up to the sun, and they're not visible from our traditional spacecraft, from our traditional coronagraphs. So anything that's around the orbit of the Earth, you cannot see these structures. And so again, this is a good sort of illustration of why it's so important to go in close to the sun. When we're out around the Earth, we're looking through the sun's atmosphere. And so there's a very nice flux rope exploding there and moving out. You can see this. So this is sort of the bulk solar wind. This is a big streamer in the solar wind, and you saw a nice detachment there. You can see some dust particles and some high energy particles, kind of specks here on the edge. But really, we're now able to see this sort of pristine solar wind because we no longer have to look through the atmosphere. One of the things is it's very dusty by the sun. It's just remnants of the initial stellar material. It's very, very dusty. And so when we look from the Earth, we are looking through the dust. And so we really need to get inside that region to be able to see these structures that we really can't see anywhere else. One of the things that we're kind of looking forward to is seeing absolutely nothing at all. What do I mean by that? As I said, it's incredibly dusty as we get close to the sun, but there's been for a long time a theory that there is a region around the sun of about maybe 3 or 4 solar radii around here that is actually a dust-free zone. But we've never been able to prove it because we're always looking through the dust. And so it's like standing on the edge of the forest and somebody says there's a clearing in the middle, but you just can't see through all those trees. And so as we get closer, we actually do expect to start seeing a dust-free region. And so I like to tease the PI that, I'm going to be really happy when you see nothing at all. And we'll finally know whether or not there is this dust-free region. And so they were some of our first light images, or some of our early images, and that movie you just saw was coming into closest approach. This is data from the ESIS suite, and so these are the high energy particles. We have two different detectors. We have a slightly lower energy and a slightly higher energy, and again that allows us to look at the full range of energies that are associated with these very sort of harsh, very transient events. So this is the higher energy, and the low energy are on the inside. It was weird, and this was our first flyby, and we saw a lot of activity in the high energies and really nothing in the low energies for a long time until we came around, and then we saw a kind of nice event here. But it was pretty quiet on that first perihelion pass. This is the second one. And so we had a nice event here, but as we came in, as we were getting to our closest approach, nice and close to the sun here, we're about 35 solar radii away from the sun right now. And this beautiful event, very high energy particle event happened. And it's kind of interesting that we saw the low energies really turn on first, and then the high energies come later. And so there's going to be a nice paper that comes out about why we see this structure. And then as we came out, you can see lots of high energy events, lots of shocks in the solar wind. And so even at solar minimum, which we're in a pretty deep solar minimum right now, you're still seeing quite a bit of activity and a lot of structure in the solar wind. So we were much happier with the second perihelion, and we're hoping the sun continues to be active. So I often get asked by people, are you worried that when you're in close to the sun, you'll see a really big event? And I say, no, I'm much more worried that we won't see one, because right now the sun is really, really quiet. And we are designed to look at the full range of solar events, and we really want to be able to look at all different kinds of solar wind, all different kinds of drivers of the solar wind. And so I'm more worried that the sun will remain quiet and we won't see something. So we are looking forward to the activity picking up. And so obviously I've talked about Gene Parker, and I've noted that the spacecraft is obviously named for Gene. There is poor Gene. He is 92 years old, and yet the poor guy at 4 o'clock in the morning let me do a selfie with him. So this is right after the launch of the spacecraft, and I got to stand right behind him at the launch. And when as it lifted off, I was able to say, "Hey, Gene, how do you feel?" And he was kind of teary. He got very emotional about the fact that we were never going to see the spacecraft again, actually. And he said to me, "Wow, we did it." And then I think he thought, obviously, maybe I expected a little more. So he looked at me and he said, "Woohoo!" And he was very, very cool and very humble about the whole thing, and just very moved emotionally about everything that was happening. I mean, this is a mission that bears his name. And so it made it a very historic event because it is the first time that NASA has ever named a mission after somebody during their own lifetime. And so when you consider that you actually have a higher probability of winning a Nobel Prize than you do of having a NASA mission named after you, this is a really, really big deal. But it made it very personal. We had a lot of media interest in Gene and the sort of the man behind it. We were kind of calling him, the physics rock star. He really doesn't like that. He's kind of humble and shy about what he's done. But we actually had a chance to take him. He came to the Applied Physics Lab right before we went in to do the testing of the spacecraft. And we actually got to take him into the clean room and introduce him to the spacecraft. And yes, you can believe I said Parker, meet Parker. But he was very, very moved by just the sheer technology that was in front of him, and gave a huge amount of credit to the engineers for making this mission that is so incredible and so amazing, make it really come to life. And, he said to me, do you know, Nikki, all I did was write a paper. And I said, yeah, it's a pretty good paper though, Gene. Don't sell yourself short. And he said, no, but you don't understand. He said, if you get in there with this mission and it turns out I'm wrong, I can just write another paper. He said, but if your engineering calculations are wrong, it's game over. And so he gave a huge, huge amount of kudos to the engineers that had really made this happen. And he said, just the astonishing feat of getting this spacecraft to do what it's going to do. And so it was a wonderful moment. I actually got to visit with him right before our 1-year anniversary and show him some of the first look data, and he was very excited. He's actually been emailing with some of the main scientists and sort of sharing in their results, and he's actually writing a small piece for us. We're going to have a Nature papers in probably November, and he's writing the sort of introductory paper for that. So we're very excited that he is still involved in the mission and still doing very well, and very happy. So a historic mission for so many reasons. Waited 60 years, first time NASA's ever named a mission after somebody during their lifetime. So it's a very, very cool mission to be involved with. And so, I talked at the beginning about how, the Earth has a magnetic field, and that actually protects us. And so if we can look maybe at the Earth and morph into the aurora, and you'll see just how our sun, our star, is really impacting us. So we live in the atmosphere of the sun. This continually expanding corona, continually accelerating away from the sun, actually bathes all of the planets. And so when the sun has an effect, we feel that here on Earth, assuming it's pointing in the right direction. And I often say it's like if the sun sneezes, the Earth catches a cold. So there's a big event that happens on the sun. It travels all the way through the solar wind, and then it comes in and impacts our planet's magnetic field. Now, our magnetic field does a great job of shielding us here at Earth. It shields us from the harmful radiation that comes from the sun. But because it's a magnetic field, it can interact with the sun's magnetic field. So as the solar wind is streaming away, it carries the sun's magnetic field with it. So it means that when it gets to Earth, that magnetic field can now interact with ours. And if you think just like like poles repel, opposite poles attract, if that solar wind field is in the opposite direction to the Earth's field, they will literally connect. They will sort of both break and reconnect with each other. And that allows an enormous amount of energy to come into our planet's sort of magnetosphere, our protective magnetic bubble. And it allows all of this energy to come down the field lines. Some complicated processes that go on, but ultimately it brings energy in which impacts our atmosphere. And it's particles that come in and they strike the atoms in our atmosphere, primarily nitrogen and oxygen, and they cause them to glow. And so they really excite these particles. I joke it's like giving a 2-year-old sugar. You bring these particles in, all these anyone with young kids is nodding right now. All of these atoms get really, really excited. They emit light. Your 2-year-old runs around like a maniac. And then once the sugar high has worn off, your 2-year-old goes back to just how they were before, and our atmosphere here also goes right back to how it was before. It's a temporary thing. We excite those atoms and molecules, and we actually cause the aurora. You can tell what kind of particles you have and how with the energy of those particles by the color of the aurora. Predominantly we see green, and that is an oxygen line. It is a single excitation state of oxygen. Sometimes you'll see red glow on the bottom, and that is what we call a double excitation state. So we've moved it up 2 so it's almost twice as excited, but that's also still oxygen. And then we often see blue, which is the nitrogen. Yes, there's the red. And so when we add all those colors together, that's often why people can say they see like purples and mauves and beautiful colors. Even yellow can sometimes be seen in the aurora. And a very, very intense aurora actually looks white because you have all of the particles, all of the light glowing and all the different colors together, and it actually looks like a strong white light. So, we get excited. The aurora is beautiful. If you've had a chance to see the aurora, it is a totally just majestic sight in the sky as these sort of shimmering curtains appear, and it looks like the curtains are kind of blowing in the wind. It's just an amazing, amazing sight. But it also tells us that there is danger in the area. So this is essentially a current structure. You have particles that are flowing in along these field lines, and there's really currents flowing in the sky, electrical currents. And so, if you remember back from your high school physics classes, currents always need to find somewhere to close. You can never have a current that's open. They're always looking for somewhere to close. If they happen to be over an area of land that is conducting, they'll just go through the earth without any problem. But if you come to an area much like the eastern seaboard here, where the rock is igneous and it's not conducting, they have to look for something else to close through. And so long, thin structures like the Alaska pipeline, the currents will flow, and obviously the aurora is seen a lot over Alaska, and so they actually have all kinds of fail-safe procedures in, so they don't think that they have a problem with the pipe. If they see surges because of these currents flowing overhead, they can also damage and cause corrosion in the pipelines. If we move down a little bit lower, then we're worried about our power grids. And so you can imagine we're looking for somewhere to close. Well, that's really nice. Not only did you provide this, but you actually provided a power system for us to flow through. And so down come these as the events get bigger and bigger. They move down towards the equator, or certainly down towards the US-Canadian border is a pretty good place to be able to see the aurora. The more intense it gets, the further down. We've seen aurora in Florida. We've seen them in Texas. And they are flowing over our power grids. And so the power that goes through our power grid is an AC. It's an alternating current, so it buzzes back and forth, and it's a pretty low voltage. When we bring these currents in, they're very high voltage currents, and they are flowing in a single direction. They are a DC current, and so now you've got a system that is used to dealing with small voltages, with AC currents, and now you put this huge direct current through that power grid, and so that can cause anything from outages to brownouts to, as we saw in 1989, there was a big event that actually knocked out the Hydro-Quebec power grid completely, leaving millions of people without power for many days. And so again, as we are more and more reliant on technology, and so we need to protect our power grids. If we lose our power grids, there is a cascading effect that we will see. The longer you lose the power grid for, the longer it takes you to recover, the more other businesses, the more other subsystems. Very soon you won't have any clean drinking water. The moment you lose power, you have no ability to move money. You've got no point of sale anymore. Everything starts to sort of implode as we start to affect more and more systems. Away from our planet. Obviously, so, we're worried about the power grids. We're worried about the long pipelines, undersea cables, anything that is prone to the aurora. As we move away, obviously, we all use satellites. We use satellite navigation. We use satellites for absolutely everything. A lot of people have the dish TV. The last thing you want is a big event to come in and take out your satellite that is carrying all of those signals. Imagine if that happened on Super Bowl Sunday. That would be terrible. And so there are a huge amount of satellites in orbit around us, and a lot of them are orbiting in and around the radiation belts. And so we sort of gets us back to the beginning of the talk, but the very first discovery of the space age was the fact that we had these radiation belts, that space was not empty. And so when James Van Allen launched Explorer 1, it had a very simple Geiger counter on, so it was counting any kind of radiation. And so as it orbited, it went through actually what turned out to be the inner radiation belt. And the first, they thought the instrument was malfunctioning, and James actually told one of his engineers, just make that signal go away. And it turned out that we had these very powerful radiation belts. They are around the equator, and they are the Van Allen radiation belts. And these belts are very, very prone also to changes in the solar wind. So as these big events come in, the radiation belts can really grow both in intensity and also in size. And so spacecraft that aren't supposed to be in these areas of radiation can kind of be engulfed by these increases in radiation. And so again, the spacecraft very, very prone to effects from the sun, either because of the direct radiation that comes with those very high energy particles. They have a mass with them. They can smash into solar panels and take many years lifetime off a solar panel. They can also cause what we call single event upsets. So they can basically have sparks. They can send currents that flow through bits of electronics in the spacecraft that are not supposed to have these currents, and you get sparks that can come, and all kinds of friction events that can cause spacecraft to change their orbits. And so there are a huge number of effects. We rely, as I said, on spacecraft every day. We become more and more reliant on technology, and therefore we become more and more prone to anything that comes to us from the sun. And that's a beautiful shot of our Earth's magnetosphere that is protecting us. And of course, our astronauts. We worry very much about our astronauts in low Earth orbit. We do a lot to protect them, to predict if there's going to be a big event on the sun, and make sure that they are not outside the ISS doing work out in the magnetosphere, but they are in and protected. As of course we support the agency's Artemis mission to return people back to the moon, or go forward to the moon, as we like to say, and then on to Mars and indeed beyond. We now have a whole different series of astronaut safety to worry about, because when they're going to be on the moon, they're going to be on the moon for extended periods. As the moon is orbiting around the Earth, it is sometimes in the magnetosphere and protected, but most of the time it's out in the pristine solar wind. And so we need to really understand what is going on in the environment of the moon, and how the sun is really driving these events. And of course, the further we go away from our planet, the more we need to be able to protect our astronauts. And so, I'll kind of leave you with the thought that what we do with Parker Solar Probe, we are sort of really it's a voyage of discovery. We're going into the unknown. We're going into a region that we've never been before. And we're going to do basic fundamental physics. We are going to go and discover the secrets of the corona, discover how our star really works. We can apply that to other stars in other galaxies. And hopefully, as we continue to search for life beyond our solar system, be able to predict which planets would be able to sustain life, and how are there stellar winds that come from other stars? Do we see stellar storms like we see sunstorms on our star? But not only are we doing this fundamental physics, but we are also really providing the last pieces of the puzzle. And this is a beautiful flare event going off on the sun here. But we are sort of doing the last pieces of the puzzle. If you think of the sun to the Earth as one complete system, we really have gaps in our knowledge. We know what is going on in the sun. We can look and we can see, we can see, hey, there's a big event. And right now we can say, well, the last time we saw that event, it caused this kind of impact here at Earth, and so statistically we can predict something. But now we're going to actually fill in that missing piece of the puzzle. What is really going on? What is the physics that is driving the solar wind? And so this is really going to make transformational improvements on our ability to predict and to forecast space weather that we have to encounter here at Earth. And so, I hope that you agree that this mission that we've done is really amazing. But, I always say, hey, that's what NASA does. I truly believe every mission, every endeavor that we do here at NASA is truly inspirational. It takes the impossible and makes it possible. It gives us our technology leaps. It gives us our scientific knowledge. And, so I, for one, can't wait to see what the future brings. So thank you very much. So it's actually pretty reflective. So about 2,500 degrees on one side. We're getting rid of the heat is about 800 degrees Fahrenheit on the back side. And so we're reflecting about probably 2/3 of the light away to stop that heat coming. So that's a really good question, and that's actually what we're hoping to find out. But we think it's in a region around about, so when we were designing the mission, we thought it was a lot closer to the sun. We've seen some data more recently where we think it's a little bit further away. So we're probably estimating anywhere from 15 to 20 solar radii away from the sun. So it's quite a considerable distance away. Originally, we thought it was around 10 solar radii, so we designed the mission to get within 10 solar radii. We're still happy we're going within 10 solar radii, but we think we'll probably see some of the raw acceleration much further out, so in some of the earlier orbits. So there are a couple of things that they can do. One is actually they can take the power grid down gracefully so it doesn't get damaged, because it's much easier to bring it up from ground state than it is to bring it up from a damaged state. And so they can actually, if it's a really big event, they can actually take down a power grid. So you'd lose power for a few hours, but you wouldn't lose power for a year. But if it's not quite such a big event, they can just maybe reroute power. They can rebalance it, so they can make sure if there's going to be a hot spot somewhere that they balance the grid better, and so that they're looking at the flow of the energy, and they can really just manage. And sometimes you take down a transformer node for a while and then bring it back up again. But again, knowing that in advance is very helpful. There's also ways of hardening it, just making things more resistant and more resilient. But the ones that are really probably more susceptible to these things are places like Texas that are not used to seeing these. So you don't harden a power grid so much in Texas because the probability of seeing it is very small. However, when you see it, it's a really big one. And so that would be one I think you would probably take the entire grid down and just protect it for maybe 12 hours and then bring it back up again after the worst of the event is over. Oh, it's microdust. That actually, Jim is probably a better person to answer about the dust. Go on.
It's micron size and smaller. Yeah, so it is very small.
Jim did his PhD in dust, so we've cleaned him off since then. So actually, that's a really good question, and that was one thing I didn't touch on when we were looking at the spacecraft. There is a big high-gain antenna that is on the anti-ram side of the spacecraft. That's actually how we communicate with the spacecraft. There are times when that heat shield is a blessing, and there are times when that heat shield is a curse. And so often the high gain is actually behind the heat shield, and so we cannot talk to the spacecraft at all. And so there are some orbits where it's very easy. Sometimes the Earth and the spacecraft are on the same side, and sometimes the spacecraft's on the other side of the sun. And so it's a little hit and miss. The first orbit, we had very, very little data that came down when we came out of that first perihelion pass. The second one, we had a great aspect angle, and we were able to bring down actually twice as much data as we had originally predicted, because we had such a good aspect angle, and we could really close that link and bring down an awful lot of Ka band data. So it's a little difficult to answer how often we get it, because it tends to be a little spurious, and each orbit is a little bit different. But we do get a bit of data down on each orbit. Most of the time it's our health and safety. It's just is everything working perfectly, yes or no? But every couple of orbits we get these really great conjunctions with the Earth, and we can just blast all the data down. The mission is designed to hold more than 2 orbits worth of data just for that very reason. So we kind of store and dump. One of the points I made was it was really great to be a 7-year mission, so we can look at the differences in the solar minimum and solar maximum, and so that's something I hadn't mentioned. But as we get into as we're in solar minimum, there are very few sunspots, and so the solar wind is actually, it's kind of counterintuitive. It's faster at solar minimum because everything is coming out of the poles, and so the poles of the sun are really open field lines, and it's a very, very fast solar wind that comes out of those. wind that is associated with the big events, with the coronal mass ejections, anything that's coming out from an active region, tends to be a slow solar wind, and it's totally counterintuitive that you really feel it should be the other way around, but it isn't. And so at solar minimum, we'll see mostly fast wind that is really driven by these holes, what we call coronal holes, open field lines coming from the poles. And then as we get towards solar maximum, we'll see more slow solar wind too. The really interesting thing is actually where you get the two streams kind of interacting with one another. So you can have a slow solar wind coming out from an active region right next to fast solar wind coming out from a region on the sun next to it, and seeing the interaction between these two is really, really interesting. And so, the 7-year mission gives us a chance to see all of these different kinds of solar wind, as well as allowing us to take those different profiles as we get closer and closer to the sun. But that was a great question. We can definitely go longer. And so I guess as the director of heliophysics, I shouldn't promise anything at this point. But when I was the project scientist, I always used to say it was a function of fuel and money for how long we could go. And so we were designed for basically a minimum mission of 7 years. We were very, very lucky with our launch. I have to give a lot of credit to ULA with that Delta IV Heavy. They put us smack down the middle of our trajectory. And so we did not need to do anywhere near as many correction maneuvers or any of the sort of little extra puffs of propellant. When we first launched, we went to Venus right on, we were within it was amazing actually how close we were to where we needed to be. So we were actually able to cancel some of those big trajectory correction maneuvers, which has given us more fuel given us more fuel than it could have done if we'd had to do everything that we thought we may have to do. And so we think we're going to have a lot of fuel. We use the fuel to basically, I didn't mention this, but we use momentum wheels to keep the spacecraft attitude. And so every now and again, we need to de-spin the momentum wheels. And so we have to do little puffs of thrusters to allow that to happen. But that's all we use the propulsion system for. And so there's a lot of gas left in the tank. And so when we get to the 7 years, assuming that all is still working, it just then becomes how much funding we have to keep the mission going into an extended mission. But there is really no reason that we could not go for another couple of years beyond that 7, given the perfect launch that we had. Oh, I came to see you guys. What brings me to Huntsville? Yes. So I came to visit Marshall. And was delighted to be able to do this at the same time. But I've had a lovely day looking around Marshall and seeing all of the wonderful facilities that are there, and it's been a good day. So we are surprised at how dynamic the solar wind is, even at this somewhat further away distance. We are seeing some phenomena that we're very surprised at. One thing is the wind is much faster, the energy of the particles is higher, and so it's a lot more dynamic, particularly given the deep solar minimum we're in. I think it's a lot more dynamic than we had expected. Certainly seeing all those whip cracks and seeing the field fluctuating dramatically close to the sun. I don't think anyone quite predicted that. So it's going to be an interesting couple of months unpacking everything that's in that data and really making sense of it. It's a challenging mission. I mentioned how fast we're moving, so we're actually approaching right now we're going at about quarter of the speed of the solar wind, and so on the way in we're sort of plowing into it. On the way out we're sort of stretching out the features. So there's a lot to look at, but really just how dynamic and how fast the wind is, even out at the distances we're at. So there's a few people scratching their heads, and a lot of people getting excited about the fact that it might prove their theory correct. So stay tuned.